Hello. Welcome to this HEEDS Technical Insights video devoted to the topic of conditional workflows and the management of partial results. This video covers advanced topics of HEEDS. As such, it is recommended that the viewer has a strong foundation in HEEDS prior to watching. The primary HEEDS feature focused on in this video is that of optional responses. However, the topic by itself is incomplete, without covering the use cases for its utilization. This is where the title, Conditional Workflows and Management of Partial Results, comes from. We will learn how optional responses can be leveraged within these two topics, but also its overlap in other advanced topics. In this video, we will introduce the motivation behind this video in the context of 3 customer challenges. These same challenges will later be solved in a demonstration. After reviewing the motivation, we will explore 4 primary topics which require an understanding before tackling their solution. We'll discuss the concept of error designs versus infeasible designs. We'll then introduce conditions and their applicability. Next, we'll introduce the looping functionality in HEEDS and its intended purpose. Finally, we'll see how all of these interact with our primary catalyst for managing the 3 challenges: optional responses. Then we'll look at the before-mentioned demonstration of the solution to the challenges in HEEDS, leveraging the concepts we've just learned about. Lastly, we'll summarize what we've learned. As noted prior, each of the topics discussed in this video are advanced in nature, and it is recommended that the viewer be intermediate to advanced in their HEEDS skill level to truly appreciate the topics, applicability, and utilization in HEEDS. Let's get started. To begin, we'll look at 3 challenges inherent in some workflows. Our first challenge involves a scenario where multiple analyses are required in a workflow. In this scenario, all analyses are long-running, and we'd like to save time if possible. Here, some analyses don't contribute to the performance of HEEDS, but are validation analyses that we'd like to perform to save us time later on with simulation data we'll need to create for our good designs, or perhaps optional advanced post-processing. For example, in this workflow, the first 2 analyses are required to judge the performance of a design at a set operating temperature. The 3rd and 4th analyses are additional analyses to be performed, but don't contribute to the optimization problem statement. The second SimCenter star CCM plus analysis is for a secondary load case we need to explore if the first is successful, say at a secondary operating temperature. Additionally, the structural performance needs to be assessed if the CFD results are promising. What is important to note here is that we don't have objectives or constraints coming out from the secondary SimCenter CCM plus analysis or the SimCenter 3D analysis. Their responses are used solely for monitoring and collecting as part of the design assessment. Since we're automating our workflow, we'd like to capitalize on the automation by executing the validation analyses, as appropriate within the HEEDS run. The challenge persistent in this scenario is that because the 2 downstream analyses are long-running and not strictly needed to judge the performance of the design, we'd like to avoid simulating them for poor-performing designs if possible. Specifically, we'd like to streamline and reduce the design space exploration turnaround time without running the validation analyses for infeasible designs. However, because there are responses tagged and being extracted from the validation analyses, we can't simply use a condition to bypass those analyses alone, because by default they will error out if the responses can't be extracted. We'll see how we can solve this challenge by learning about the importance of non-error designs and learning about and leveraging the necessity for a runtime condition in combination with optional responses. Before doing so, however, let's review some other challenges we'd like to learn how to address. The second challenge posed in today's video is an extension of the idea posed in the first challenge. Here we have analyses that only have to be executed some of the time due to conditional if-else branches being required. As with the first challenge, here the problem stems from the fact that results won't always be available since the given analysis won't always be run. The solution to this problem, however, is different from that of the first due to the difference in when analyses are executed. Here we have a workflow with a conditional branch that determines when to run one CFD analysis versus another. Unlike the first challenge where an analysis either runs or it doesn't, here if an analysis isn't run, an alternative needs to be run in its place. For example, here following the conditional if-else branch, either scenario 1 is run or scenario 2, depending on the results from an upstream Python analysis. As an example, this could represent where scenario 1 models laminar flow and scenario 2 turbulent flow. We'll see how we can handle this situation by tagging the same responses in both SimCenter* CCM plus analyses. Under this special if-else conditional branch, HEADS allows duplicate tagging of responses, such that, regardless of the scenario run, the results will be available and stored to the response. A runtime condition, like in the first challenge, dictates when an analysis is run. Here, that condition exclusively allows for scenario 1 or scenario 2 to be run. As such, the difference now is that the response will always be available, so long as the condition definition ensures it. If indeed that is the case, then an optional response is not required to manage this challenge. Our third challenge is inherently different from the first two, where now instead of choosing when to run an analysis, we need to determine how many times to run it for a given design. In this scenario, we need to run an analysis or multiple analyses multiple times for each design iteration to truly assess each design's performance. Use cases could include execution of the analysis multiple times to ensure convergence, to execute a decoupled co-simulation, amongst other reasons. Here, we have a workflow where the CFD simulation needs to be run multiple times for each design. Perhaps, for example, the position of the part needs to be altered incrementally to assess various load cases, such as assessing angle of attack performance. The challenge now becomes how to manage the results being extracted for each iteration, and if applicable, how to handle them as input into the next iteration. The HEADS looping functionality facilitates this, in combination with run conditions and special response handling under certain scenarios, as we'll learn. So what do all three of these challenges have in common? They each involved advanced workflow orchestration, where conditions play a key role. There is the possibility that without careful handling, the results won't be available. This is where optional responses come into play. Lastly, there is the strong possibility that without proper handling, the designs will be marked as error designs. Both run conditions and optional responses in tandem can help ensure this isn't the case. With the foundational motivation established, let's start to look at each of the key ingredients necessary in solving these challenges. Before doing so, however, let's first understand the importance of leveraging these features such that errors are not incorrectly introduced and the ramifications if they were. To understand why we must carefully handle responses to avoid error designs, we must first fully grasp the difference between infeasible and error designs. Infeasible designs are valid solutions resulting from successful process execution in HEADS. While valid, that does not mean they are good performing solutions. In fact, if infeasible, this indicates they did not meet one or more of the specified requirements, or constraint thresholds in optimization terminology. In the context of HEADS, an infeasible design specifically indicates the following has occurred for the given design. The portal-specific requirements were met, the required responses extracted, any success conditions passed, and the extracted response values don't meet the requirements. The latter being the only difference between an infeasible solution and a feasible solution, where the requirements are all met. As such, the performance for infeasible designs is calculated, and the performance metric used to judge that design's performance relative to the other designs evaluated. As shown here by the performance function used in HEEDS, the amount of constraint violations penalize a design's performance. The computed performance for each design provides the foundation for the search decisions, allowing HEEDS to properly navigate a design landscape during an optimization and efficiently find innovative solutions to your problem. Contrarily, error designs, on the other hand, represent invalid solutions. They can result from modeling limitations forcing one or more process failures. Additionally, they can be imposed by the user to ensure engineering and design considerations are met to automatically capture scenarios where a valid simulation may have run, but it resulted in an invalid design. A common example resulting in error designs includes scenarios where the CAD couldn't regenerate. Here we see a fillet radius imposed, where its applicability is limited by the length and height dimensions for the two surfaces it is joining. If it becomes too large relative to the other dimensions, the geometry will fail to regenerate, resulting in an error. Another example of an error design is when a solution diverges. Here, even though the simulation ran, the results are invalid as the solution isn't fully resolved. Similarly, when a solution completes but its solution isn't valid, is another scenario where the design should be marked as an error. In explicit dynamic finite element analysis, this can occur if too much artificial energy is introduced into the design due to mass scaling. There are also scenarios where designs need to be marked as errors if they could never be produced or manufactured. For example, if this layup requires that t is a constant value, but the variable combinations of t1, t2, t3 for a given design don't total the required total thickness t, it violates the possibility to make the part altogether and is an invalid design. In the context of HEEDS, error designs can result from portal-specific requirements not being met, required responses not being extracted, success conditions not being met, or response values being outside a prescribed validity range. Note that the last bullet point is different than a constraint threshold, where HEEDS allows the ability to provide validity ranges separate from performance criteria. The important concept to remember is that error designs do not have their performance computed by HEEDS. Rather, error designs are all treated equally, meaning HEEDS doesn't distinguish the quality of their solutions at all. It simply determines that because the design was an error, it will never be evaluated again. Inherently, due to Sherpa's focus on innovative solutions, error-prone regions in the design landscape get ignored as the optimization progresses. Error designs introduce discontinuities into the design landscape, making efficient search challenging. As such, with HEEDS and Sherpa, we recommend targeting less than 30% error designs during an optimization. Stated inversely, 70% of the design landscape or more should be targeted to be valid solutions. Why is understanding the difference between infeasible and error designs important? Because with this knowledge, we can formalize ways to ensure proper handling of complex workflows to manage proper designation of designs between these two categories. With this understanding now established, we can venture into how to manage complex workflows to avoid improper error designs. The first feature we'll look at is termed conditions in HEEDS. Conditions are used to define a logic for which assessment of the state of the object for which it is applied can be assessed. Conditions may be dependent upon files, responses, variables, upstream analyses, and can be leveraged in different ways with if-else definitions. There are three types of conditions in HEEDS. Finished conditions can be used to determine whether an analysis is complete or continues to run. Upon completion, this signifies to HEEDS that the analysis is done and the next steps related to the analysis and/or workflow can commence. Success conditions define whether the completed analysis was successful, a valid design, or unsuccessful, an invalid design that should be marked as an error. Lastly, run conditions, which are the focus in this video, determine whether or not an analysis should be executed. For example, from the second challenge shown earlier, a condition, represented by the flowchart diamond here, determines whether Scenario 1 or Scenario 2 should be run for the given design. Here, opposite run conditions are used to run either Scenario 1 or Scenario 2 for a design, meaning the two CFD analyses run mutually exclusive. Results are pulled from each analysis with duplicate tags, a special capability with mutually exclusive conditions. For non-mutually exclusive conditions, error designs can be avoided using optional responses with care. Let's now look at the feature called looping in HEADS. Looping is a key functionality within HEADS that is critical to accomplishment of certain advanced aspects of workflows. Examples include the following: assessing a design over multiple load cases within a single analysis portal in HEADS, performing a task until a certain threshold is attained, such as mesh convergence, and iterating until a simulation model converges. Additionally, looping can be used to run loosely coupled co-simulations, where iterative data transfer between analyses must occur until a threshold is attained. Note that here we are describing loosely coupled co-simulation as opposed to more fully featured coupling achieved through definition within the simulation tools themselves. Generally speaking, the purpose of using a loop is to run a portion or all of your process multiple times for each design evaluation. To achieve this, a single parameter is defined, which is a loop iterator, or the variant that is changing within a design. Conditions can be used to ascertain when the looping should stop for the given design. Whereafter, the relevant results can be collected and utilized with various options to control their storing and passing on further downstream into the workflow. This last aspect is where management of results becomes crucial, as it pertains to our video. Results can be defined, default values, whether they are required or optional, and have the ability to update and overwrite prior results for a given design. Partial results get managed with a feature called optional responses. Before looking at optional responses, let's begin by focusing on responses themselves. Responses are defined as output extracted after analysis execution from a simulation tool via tagging, or computed via the HEADS formula editor. Responses can be used to define the goals of the study via designation as objectives or constraints, can be used to specify error thresholds, can be used for condition criteria in downstream analyses, or can be used simply for monitoring results. Additionally, responses can be used as inputs into dependent variable calculations or formula-based response computations. Lastly, responses can be used as input into downstream analysis. By default, if a response is defined, it is required to take on a value from the workflow from the analysis from which it is designated. If it cannot be extracted or computed, it is considered to result in an error for the designated analysis by default. This takes us to where optional responses come into play. An optional response is a response which does not trigger an error if not retrievable. As the name implies, when the user utilizes this feature, they are designating that response to no longer be required, but rather optional. This utilization also allows for providing a default value for the response. A default value means that the response has a starting value that either gets overwritten if the response value becomes retrievable, or remains at the default value if not. This option allows for passing of data, as appropriate with default values should no value for the response be extracted or calculated as part of the workflow. Optional responses are what allow for the management of missing or partial results in an automated workflow. If we return to the workflow for responses shown earlier, We can use it to understand what limitations exist with optional responses and what we mean when we say they must not be strictly needed. First, an optional response must not be tagged into a downstream analysis. Second, it must not be used within another required response, such as a formula. Lastly, it can't be used in the performance function of an optimization, meaning it can't be used as an objective or constraint. So, how can optional responses be used then? They can be used for responses used solely for monitoring, as in our first challenge scenario. Additionally, they can be used in complex workflows with special handling. They can be used as key ingredients in utilizing loops and certain conditional analyses to avoid incorrect errors. Let's look at how all of the concepts explored in this video can be implemented in HEADS to address the three challenges we saw at the beginning of this video. Recall the first challenge we seek to address involved optional validation analyses, which are long-running. We desire to avoid running these costly analyses for infeasible solutions, but reserve them only for promising designs. Let's see how to implement this in HEADS using the concepts established in this video. Here we have our workflow already built, with our optional analyses grouped together in an analysis group labeled Validation Group. With no special handling, when we execute this workflow, all designs run the validation analyses as part of their orchestration. To save time, compute resources, and licenses, we desire to only have the analysis validation 1 and the analysis validation 2 only run when the CFD analysis is feasible. Let's alter our workflow to achieve this. There are two primary features we need to leverage to achieve our goals. Firstly, we need to implement runtime conditions for our two validation analyses that enforce a conditional branch for when they are to be executed. The condition manager can be leveraged to define the appropriate condition. In this case, the condition will be based upon the feasibility of the CFD analysis, as we define here. With the condition defined, it can be applied to both validation analyses as a run condition. Conditional graphics appear on each analysis to visually confirm for the user that a run condition is applied. With this implementation, when we run the design space exploration, we now see that the analyses are only executed upon feasibility of the upstream CFD analysis. If the CFD analysis is infeasible, the downstream validation analyses are now skipped. However, we still have an issue with our workflow. Whenever the validation analyses are skipped, the design results in an error, since the responses tagged within the validation analyses cannot be extracted. We can confirm for our workflow that the responses from the validation analyses are not used as objectives or constraints, and therefore have no bearing on the design performance. This is intentional, as denoted earlier. We only desire to run these analyses to collect additional information for designs we find promising, but do not wish them to impact the judged design performance as part of the design space exploration. So how do we avoid the designs not running the validation analyses being marked as errors? By going to the respective responses coming from the validation analyses, we can expand the response properties and alter the response from being required to optional. If desired, a default value can be supplied to the response as well. Recall, this is a placeholder until the response is overwritten during execution. If the analysis is skipped, the response will retain the default value for the given design. With this additional modification, now the workflow runs as desired. We can confirm that for the skipped analyses, no responses are available, yet the designs were still successful. Our conditional workflow is now established. Our second challenge is similar to the first, in the fact that analyses need not always be run. However, this second workflow is different in the fact that now, depending on the upstream condition, either analysis 1 or analysis 2 must be run. Additionally, in this case, the same responses come out of each analysis, requiring special handling. Here we have a workflow established for our challenge. Like before, the first thing we must do is establish a run condition that properly handles the conditional analyses. Here, a response value being extracted from the upstream Python analysis determines whether to run scenario 1 or scenario 2. A run condition is created and applied for scenario 1. And the opposite run condition is defined and applied to scenario 2. As such, only scenario 1 or scenario 2 will be executed for a given design. In this case, our responses are not optional responses, but rather required. HEADS has special allowance during tagging to ensure that regardless of the scenario run, the response can be available as output. This is established through the allowance of tagging the same response multiple times for analyses with conditions applied to them, to allow for conditional workflows. Tagging is done as normal, but now the responses of interest coming from scenario 1 and scenario 2 are tagged from both respective output files. Normally this isn't allowed. However, as noted, special handling ensures for conditional analyses this can occur. If we examine the response of interest, we can see under the properties that indeed it is associated with each analysis. At runtime, we therefore see the proper execution of this conditional workflow, where either scenario 1 or scenario 2 is executed for the given design, while the relevant response is extracted and stored accordingly regardless of which scenario is run. The last challenge we will solve involves leveraging aspects of what we've learned so far, as well as a unique capability yet to be explored. To manage mesh convergence for each design as part of a design space exploration, we'll leverage the looping capabilities of HEADS. As part of the looping implementation, we'll utilize a condition in a unique way, as well as a default response value. Here we have our workflow defined with a loop already implemented. We'll review the pre-configured setup in detail, rather than set up the project from scratch. We can see the add loop functionality has already been leveraged around the SimCenter Star CCM plus analysis portal. If we click on the loop, we see special execution and output options specific to the loop. This overlays the settings defined for the given analysis, done as normal. Under the loop execution, we see that a discrete source type is used to define the loop iterator. In this case, as opposed to a continuous variable or a parameter list, a project-defined discrete set prescribes the iteration values applicable to the loop iteration. In this case, the discrete set includes 4 mesh sizes as iterators. The order of the sizes are listed from largest to smallest, aligned with our goal to assess the design performance at the largest mesh size applicable for the given design to give suitable mesh convergence. We'll look at what suitable mesh convergence means shortly. In addition to the loop iterator or loop values source, we also must define the loop execution options. We have defined here that if an error occurs, the loop process should stop. Secondly, we've defined that only one case within the loop for a given design can run at any given time. This parallel execution option is of utmost importance for our case, since each loop iteration is dependent upon the results of the previous loop iteration, as we'll see. With the loop execution now understood, let's take a look at the loop output. As the name suggests, the loop output defines how and when to store the results for the loop. In our case, we need to note 2 important aspects. First, the response values are set to be stored when a defined condition is satisfied. In practical terms, we are telling HEADS to store the results for the iteration where mesh convergence is deemed to have occurred. This is done through the definition of a condition, which is monitoring the difference in the response of interest, shock volume here, from one iteration to the next for the given design. Stated differently, when the results vary below a prescribed threshold, the mesh fidelity is considered converged and the looping stops. Comparisons between results are made from one mesh size to another, and a difference computed in a response called delta shock volume. Recall that from one loop iteration to the next, the mesh is progressively refined. When comparing results for the given mesh size with that from the prior mesh size, if the difference is smaller than 0.0002, in this case, we consider the solution converged. The option Stop when satisfied ensures that the looping is stopped when the condition is reached. If we investigate the response delta shock volume, we can confirm that this formula-based response indeed computes the difference between the tagged output for the given iteration and that from the prior, which is stored through a dependent variable shock volume 0 in this case. Note that it is important that this shock volume 0, while computed for a given iteration, must also be tagged as a dummy tag to ensure its value is available at the start of the given iteration. Here, we've done so to a text file that does not impact the actual simulation, purely as a mechanism to initiate the value from the past iteration into the given iteration. The last critical piece of information required to make this workflow run seamlessly is to define a default value for the tagged response shock volume. This is required since our stopping criteria is based upon the difference between the current iteration and the last. For the first iteration, there is no last, and thus a default value is required to ensure computation is possible. If we look at the results for a DOE study, run with this workflow, we can see that the mesh size where convergence occurs changed from design to design. If we go to the Response Explorer tool, available under the Investigate tab in HEAD's post, we can further see the iterations within the loop for each design. For each design, we see that once the delta shock volume is less than 0.0002, the iteration stopped and the results were collected for the deemed converged solution. Looping in combination with other advanced workflow items like conditions and default response values is another way to implement certain conditional analyses, as we've just seen here. Having successfully solved our 3 challenges, let's summarize what we've learned in this video. Through 3 scenarios related to conditional workflows, the management of partial results and complex operations, we presented various topics within this video. We later solved those challenges using the topics presented in a live demonstration within HEADS. We can conclude that optional responses and conditions allow for advanced workflow orchestration, the management of scenarios where results won't always be available or can fork in the analysis from which they reside, and finally, in ensuring unnecessary errors are not introduced as part of complex scenarios. Looping was introduced as a special case under this conditional workflow umbrella as well, where other aspects learned come full circle in implementation with a loop. Thank you for your time and attention in learning about these important topics. We trust you are better equipped to manage complex workflows within your automated HEADS workflows moving forward. We encourage you to keep learning and taking advantage of the various self-learning resources made available to you from the HEADS team. Thank you for watching.